Now it is. So our goal today is to solve integrals with infinity
Good luck you meet.
in the bounds.
I hope you swim like a fish. Or a dolphin.
It's already over, bro.
Well, that's okay.
Why not a mermaid?
When I went to Miami.
Mermaids are faster.
Than a fish?
Says who?
No way. Fishes are much
This
faster.
is every fairy tale.
What are you trusting, Disney?
Improper.
Yeah. Yep, improper integrals.
So that's when you mess up.
No, it's when they're not British.
So, when really all an integral is, an improper integral is an integral that has infinity in its bounds. What if we don't want to go from 1 to 5? What if we want to go from 1 to infinity?
Well, that sucks for you.
Okay, so there's two main cases. Our first case is something like this. If I start at 1 and I take the area forever,
You're right, that did take forever.
what's my area going to be? So if I integrate this function from 1 to infinity, and I'm going forever, how much am I adding as I get bigger?
Infinity.
More and more and more. So this one would be infinity. I have an infinite area. But what if I have one that looks like this? Still start at 1. Good.
Not even good.
Oh, dx. So if I integrate this from 1 to infinity, what's going to happen as I go to infinity?
Gets to 0.
Gets to 0. Eventually we're adding 0 over and over again. You know, technically it's 0.0000000000000 whatever, but that's such a small amount, it might as well be 0. So
Or amount.
it gets infinitely small.
All those
So
strings.
this would equal some value. Let me call it AL.
Or
Doesn't
some
really
value.
matter. Some value. We don't know exactly what the value is, but eventually we're adding a small enough amount that this actually does equal something. One of my favorite things in calculus is called Gabriel's horn. I should have looked it up again before I talk about it, but if you take this shape and revolve it around the x-axis, you can either paint the surface but never fill it up, or fill it up but never paint the surface. Like mathematically, one of the integrals works, but the other one doesn't. I'll look it up and show you next time for sure, but I always thought that was pretty cool. I'm like, that's impossible!
That was impossible.
Okay, so our goal when we do this is we can't actually integrate if infinity is involved. So we want to do something to get infinity uninvolved with our integral. So with all of them, we're going to change it so we're taking the limit, and we're going to, what's normally here instead of infinity on the first one?
B.
B. So we're going to say as b approaches infinity, we're going to take the limit as we go to infinity of our integral. And a will be some number, but b is literally going to be the letter b when we integrate. We're going to integrate and use the letter b in our fundamental theorem of calculus. And then we have to take the limit after we integrate. Same thing if we're going from negative infinity to b. So this time we'd say a approaching negative infinity from a to b. And this time we'd actually have the letter a involved, but b would be whatever number they gave us originally. And then our last one, we'd actually have to split this integral up. If we're going from negative infinity to positive infinity, we have to split our integral because we can't have a limit approaching negative infinity, and a limit approaching positive infinity. So we'd have to have the integral from negative infinity to c, because c is whatever point we're choosing to split it up at, f of x dx, plus the integral of c to positive infinity, f of x dx. And then with both of these, we'd have to apply the limit formula as well. We'd have to say the limit as a approaches negative infinity of a to the c f of x d of x plus limit as b approaches infinity of c to b f of x dx, which we're not going to write the second one down. This last case doesn't come up as often as these first two. So let's see this in practice. It's actually on the next page. So let me wait for everyone to have this written down.
Everyone thinks
Do not eat lunch during lunch.
why would you eat lunch during lunch?
No, I was going to, but then my friends were like, hey, come with us, we'll pay for your food. So I eat pizza during lunch and I'm eating my lunch during this class.
Okay, so here's our first example. So this is why in the warm-up we practice U sub, integration by parts, partial fractions, because we're going to have to know all of our different ways to integrate when we do this. But first, I cannot integrate if infinity is there. So we have to change it first to say the limit. Are we doing A or B in this case?
A. Wait. B. Wait, is it?
Yes. B.
B.
It's sometimes hard to remember which one's A, which one's B. So limit as b approaches infinity, the integral from 0 to b, e to the negative x over 2 dx. So we get to ignore the limit for a while. We're going to have to keep writing it so that we get practice writing it, even if we know, hey, I don't have to use this right now. But now we can just integrate that stuff. So what tactic would we have to use to integrate this? We have anti-power rule, we have U substitution, we have integration by parts, and we have partial fractions. When do we usually use anti-power rule? When it's a polynomial. Okay, usually we use that when it's a polynomial. What about U sub? When do we usually use U sub?
Something squared or the square root of something.
Okay. Something squared, square root of something.
Trying to get something to cancel.
Yep. When do we normally use parts? Tabular integration, same thing.
when you have
You have two functions that are multiplying. It's anti-power rule. And when do we usually use partial fractions?
Yeah,
there's a fraction.
And fraction. So which one's most likely to fit this situation?
partial fraction.
We don't have, well, when we have partial fractions, we have a big fraction, not a fraction in the exponent.
U sub.
U sub.
I think that's the first time
We
I
don't
raised
have
my hand.
two functions. It's not a polynomial. It's not a big fraction we can work with. Probably U sub. What would we pick to be U?
I shared my pizza. It wasn't
But not
mine.
with me.
Yes. What should we pick to be U?
E. Negative x over 2.
Negative x over 2.
Oh, eat that.
Or I'm going to write it as negative 1/2 x to make it easier for us to take the derivative. So then we want to know what dx equals. Dx would be du over the derivative of this. What's the derivative of negative 1/2 x?
Negative 1/2.
Negative 1/2. Or, flipping that to the top, negative 2 du. So now we can go make
Oh,
our
so two
replacements.
fractions
So we replace negative x over 2 with u. We replace 2x with negative 2 du. And now we can actually integrate. What's the integral of negative 2e to the u? Negative 2 is just a coefficient. I really could bring that out front. So what's the integral of e to the u? E to the u. That is something we should
E to the U.
get memorized.
No, that was late. I wasn't listening. I was like writing down and then I realized what she asked. I was like, oh, yeah.
It was wonderful timing.
So we have negative 2 e to the u, except we want x back in. If we're going to apply those bounds, we're going to plug negative x over 2 back in, from 0 to b. And now we have to apply the fundamental theorem of calculus. We have to do f of b minus f of a. So everywhere I see x, I'm going to replace. Negative 2 times e to the negative b over 2 minus e to the negative 0 over 2. And now, if possible, I can apply my limit, or we could clean stuff up first, kind of whatever you prefer. So what could we clean up?
And then you did the negative 0 over 2.
What's e to the negative 0 over 2? 1. So we have, and I'm going to distribute the negative 2 as well. Limit as x approaches infinity, negative 2, e to the negative b over 2, plus 2. So now what would happen if we plug in infinity? Negative 2e to the negative infinity over 2. What happens when we have negative infinity as an exponent? We saw this.
You had to move it down.
It's really on the bottom, so what is that really when we have e to the negative infinity? 0. So anytime we have a number to the negative infinity, or any version of negative infinity, that's really 0. We could go through the process of rewriting this as 1 over e to the b over 2, and then say 1 over infinity, which is 0. But we're trying to save ourselves a little bit of time, so if we try and remember e to the negative infinity, that's the same as 0. So really we have 0 plus 2, which is 2. Now it is possible for it to diverge instead of converge. If we go through this whole process and we go to take the limit, what if our limit had been e to the b over 2 plus 2? Okay, so we still have the negative 2 out front. What happens when we plug in infinity? What's e to the positive infinity? Infinity. What's a negative number times positive infinity, though? Negative infinity. So this whole integral, if it had come out positive instead, would equal negative infinity. It wouldn't actually converge to a limit. So it is possible for us to not get a number as an answer, but to get infinity as our answer. So I have one. I'm going to have you guys try.
Absolute disaster.
Okay, so we're going to finish this try problem, and then I'm going to adjust the assignment. We were going to get to a little more today, but we were splitting this into 2 days anyway, overall. So, dx over x really is 1 over x dx. Before I can integrate, I know it seems silly, but I must write this as limit as b approaches infinity. If you did not do this and you just integrated right now and used infinity like a bound, well, not after you integrated. If you integrated and did fundamental theorem of calculus, you'd get pretty much the same thing. But on the AP test, if this were a free response question and you don't write that limit as b approaches infinity, then they won't give you the point. So, oh, sorry, not 1 to infinity, 1 to b. And we did have to remember the integral of 1 over x. What is that?
Oh, lin of x.
Ln of x.
Rolling what?
Now, one thing I saw most of you forget, though, is it's ln absolute value of x. That won't change your final answer on this question, but it's good to remember it every time in case it does change your answer. So then, fundamental theorem of calculus says limit as b approaches infinity of ln of absolute value of infinity minus ln of 1. Man, my brain on this problem is not wanting to leave b. Okay, ln of b minus natural log of 1. And now I can apply the limit and say ln of absolute value of infinity. Ln of 1 really is 0, so we can ignore it. And what is the natural log of the absolute value of infinity? Infinity. So homework-wise, sorry again, I'm changing it, so it might take a second. So again, we're almost done with chapter 9. The nice thing about it is it'll be hopefully a boost to test scores for you guys, because it's not the hardest chapter in the
Book,
book. Yeah.
like last chapter.
Let's see.
I have a certain way.
And I do want you to show the work, show the integration, because we need to practice our integration by hand so that we don't forget how to do that.